it's time for the big finale to Chapter 2, Section 2.9 on the formal definition of a limit. So, let me just preface this, that this is a topic that's going to be very different than everything else that we've done so far, that we're going to be doing things rigorously, we're going to be actually proving things, and so I say that not to scare you off, but just to make you realize this is something that's going to take a bit of time to get used to. This is a section you'll probably want to spend a lot of time thinking about, working through, practicing, thinking about this. So the formal definition of a limit. So recall, I already wrote this up, back in section 2.2, when we first introduced limits, we had what I called at the time, this wasn't the authors of the textbook's term, but we had a semi-formal definition of a limit. So what's going on here? So here's the prologue. We say the limit as x goes to c of f of x is equal to L if the absolute value of f of x minus L can be made arbitrarily small by taking x sufficiently close to c, but not exactly equal to c. And so why is this semi-formal and not formal? Well, we use the phrase arbitrarily small and sufficiently close. And so we want to be able to come up with a way to precisely say what does arbitrarily small mean, and we want to come up with a way to say what does sufficiently close mean. And so in order to do this, we're going to talk about the key quantity here is going to be the absolute value of f of x minus L. So the authors of the textbook, they're going to call this the gap. So the gap is the absolute value f of x minus L. It's how far, it's the distance from f of x to L. And our goal, remember, is to make this small. So, drawing out a picture and stuff like that here, if we are here at C, we're trying to show that the limit is equal to L. Our goal is if here is our f of x, if we're at some value of x that's close to C, we want f of x minus L, which is that teeny tiny distance there. Absolute value f of x minus L, we want that to be small. So let's think about how this looks like, what this game of making the gap arbitrarily small by taking x sufficiently close to C looks like. And so I'm going to steal the same example that the authors of the textbook do. I'm going to use their example, which is, let's think about what is, once again, the fact that the limit as x goes to 0 of sine x over x is equal to 1. So here, f of x is sine x over x. L is equal to 1, and so our gap is the absolute value of sine x over x minus 1. This is the thing that we want to make small. So going back to this here, we want to, so reading off the definition, if the gap, absolute value of sine x over x minus 1, if the gap can be made arbitrarily small by taking x sufficiently close to 0. In this case, our limit is being taken close to 0. So we can make this arbitrarily small by taking x sufficiently close to 0. So how arbitrarily small? What does arbitrarily small mean? It means that if I choose a particular positive number, you can make it smaller than that. So for example, I could choose that I want the gap to be less than 0.2. So arbitrarily small, I can have any choice that I want to. Right now I'm choosing that I want the gap to be smaller than 0.2. That I want the absolute value of sine x over x minus 1 to be less than 0.2. And so now the question is, how close to 0 must x be? So sufficiently close. So how close to 0 do we have to choose x to be? Does it have to, if we want their gap to be within 0.2? Do we have to choose x to be within 1 of 0? Do we have to choose x to be within 0.1 of 0? Do we have to choose x to be within 0.01 of 0? That's what we're about to ask right now. How sufficiently close is sufficiently close? How close is sufficiently close? Well, if we play around with pictures and stuff like that, so here I'm zooming in on here, that according to this picture, that if we choose x to be within 1 of 0, then the gap is always less than 0.2. Let me write that out and draw that. So the assertion is that if x is within 1 of 0, then the gap is within 0.2 of 1, which is the limit. That's writing things out in words. I could write this out more symbolically and say, if x minus 0 is less than 1, then the gap sine x over x minus 1 is less than 0.2. So, drawing a picture here, gonna have to get a new black marker before too long, I guess. So here is 1. Here is sine x over x. And so the assertion is, if here is 1 and here is minus 1, so the allowable x values that we have, or the values between 1 and minus 1, every output value, so the output values are, these are the output values, that like 0.8 is right there. So all of the output values are at least 0.8. So all of the output values, if x is between minus 1 and 1, are within 0.2 of our limit. Okay, so before we were saying that we can make this arbitrarily small. And so what we just did was that we saw pictorially that if we wanted the gap to be less than 0.2, that here's a choice that we can choose x to be sufficiently close to 0, x to be less than 1, and that takes care of this gap. But arbitrarily small means, well, I could have chosen something else instead of 0.2. So instead, if we want the gap to be less than 0.004, here's a different gap, that we want, an even smaller, arbitrarily small gap here. Then, if we look at the picture, we can see that if absolute value of x is at least 0, but less than 0.15, then the gap sine x over x minus 1 is less than 0.004. So let's just see once again on the picture here. So now we're zooming in really tight. We've chopped the interval down from -1 to 1, down to -0.15 to 0.15, and now all the output values are at least 0.996, so the gap here is always going to be less than 0.004. So once again, if I told you, I said, here's how small I'm demanding the gap to be, you can say, okay, here's how close to 0 I can make x to say this will be sufficiently, if x is this close to 0, if absolute value of x is less than 0.15, then we can satisfy the gap condition. So I tell you how small I'm demanding my gap condition to be. You're giving me this condition, this range of x values that will make the gap condition be small enough. And so putting all of that together, we have, instead of having the definition of the semi-formal definition of the limit, we're going to see now the formal definition of the limit. So what's going on here? Suppose that f of x is defined for all x in an open interval around c, but not necessarily at x is equal to c. So before, our c was 0. So it's defined around 0, but not necessarily at 0. Then we say the limit as x goes to c of f of x is equal to L if for all epsilon greater than 0, there is delta greater than 0, such that if absolute value of x minus c is between 0 and delta, then the absolute value f of x minus L is less than epsilon. So this might look scary at first glance. This is all standard prolog, so the new things here are this epsilon greater than 0, the delta greater than 0, and these two inequalities here. So it's actually things that we just dealt with. So this, for all epsilon greater than 0, this is going to be how small I am demanding the gap to be. And so then this delta here, this is how close to C should we be. So in the previous things that we just did, let me pull back this one here. So this 0.2, that was epsilon. I chose epsilon. I want the gap to be less than this epsilon here of 0.2. This one here was the delta. It's how close to 0 do we have to be. So if for every choice of how small we're demanding that gap to be, we can say this is how close to C that we have to be. Here's where we're saying this is how close to C that we have to be, and this is where we're saying the conclusion. Then, if we're this close to C, then our gap condition is small enough. So that's the formal definition of a limit, and this has already been a long enough video, so in the succeeding videos, we'll see what happens when we actually prove that limits exist using this epsilon delta definition.